PhD defense. This has been quite a few years in the making, but he finally was able to pull it off. And so he'll present today the final results that are in his dissertation. And we'll have the open session first, where all the guests can listen in and ask questions, and then we'll excuse them and proceed to a closed section, Cory, which I believe you have the host capability, so you'll just need to get them to leave the meeting before we commence with the closed portion. And I don't know if Pachiro, as the dean's rep, that for virtual defense, did you have anything you wanted to add in?
Not really. I mean, well, the rules I think we know, and I think you just spelled out the procedure, and we'll go by that. And I just claim that I'm the dean's rep, which I'm supposed to do. Yeah.
Okay. Well,
actually, I'm sorry, just to interject really quickly. I think one thing you do have to announce is that the presentation is being recorded.
Oh. Yeah. Right.
Actually, I don't think we're supposed to record these.
Well, I think you can. I don't believe there's anything prohibiting it. But if you're going to, I think you do have to make a formal.
Well, you do have to make the announcement, but I just noticed it was being recorded. And so, Cory.
Yes, sir.
Do we have to record this?
We don't have to. I had some reasons that I might want to,
There's reasons that you want to?
Yeah, share this with some other people who maybe weren't able to make it to this session.
So
all right. Well, then
what I've seen done is one of us or Cory ask everybody if it's okay to record, and if everybody nods or gives thumbs up, you proceed with recording. And it was recorded in some of the ones that I attended.
Right. So we'll ask everybody, Cory, does anyone object to the recording of this?
Yeah, any objections to having this being recorded?
I don't have an objective to the public part being recorded.
Oh, the private one we won't be recording.
Okay.
Don't do that. That's not done ever.
Yeah, no, just this public portion. That's all.
Okay.
So the only other issue we'll have is hopefully people don't join in and don't realize that it's being recorded. So that's the only other issue you run into. But you might, I don't know, if you notice somebody, you might just announce it as you go through. So I think everybody kind of gets Zoom fatigue. I'd rather Cory be doing the talking, so I'm going to turn it over to him now and let him begin his defense.
Yeah, that sounds good. So good afternoon, everyone, and thank you, Dr. Bruck, for the introduction. The PhD dissertation topic that I'm presenting today is entitled Fabrication and Characterization of Nanoscale Shape Memory Alloy MEMS Actuators. So I'm currently a mechanical engineer at the U.S. Army Night Vision and Electronics Sensors Directorate. And I'm in the Imaging Technologies branch within the Science and Technology Division, where I continue to work in this area to develop adaptive imaging systems based on phase change materials and MEMS. But as Dr. Bruck said, this dissertation was primarily conducted during my 6 years at the U.S. Army Research Laboratory. And I owe special thanks to you, Dr. Bruck, and Dr. Chris Morris for helping to guide these efforts over this time. And finally, I want to just give a special thank you to the dissertation committee for taking your valuable time to review the dissertation and for being here for the defense. So in this defense, I'll start by providing a motivation for developing these miniaturized phase change microactuators capable of large and fast deflections. I'll present some insights from a literature review that highlights some of the existing microactuator materials and discuss why SMA was chosen for this dissertation and where there exists room for improving state of the art. This will lead into the 4 main scientific and technical contributions, which detail the miniaturization of nanoscale SMA materials capable of exhibiting reversible phase changes, at increased frequencies compared to existing state-of-the-art. And finally, I'll summarize how these developments were documented in a variety of journal publications, book chapters, and an invention disclosure. So the motivation for this PhD dissertation was to develop high-speed SMA microactuators and micromirrors for microrobotics and adaptive imaging systems, which would ultimately find utility in various DoD and commercial applications. So some of the fundamental requirements for these novel microactuators would be to enable shape memory effects in nanoscale films that would be able to enable extremely large and fast deflections. So the actuation should be such that an active electrical source could provide this input, or a passive laser source could also be used to induce the thermal actuation. Other desired features of the actuators would be low power consumption to enable applications to be scaled down into power constrained environments, for example, on computer chips. So the figure here on the left shows a micromirror array in the open and closed configurations and operating based on a reversible phase change, which helps to motivate the exploration of these nanoscale SMA films. So when first embarking to design the high-speed microactuators, I had initially considered many of the classes of microactuator materials available, some of which are shown and compared here. I ultimately chose the SMA actuator for the mechanism for actuation for its inherently high energy densities, meaning that for a given volume of material, SMA can provide some of the highest combination of forces and displacements, which will be most suitable for these proposed large deflection micromirror applications. So as shown in the figure of energy density versus actuation frequency, the NiTi-based SMA MEMS yield some of the highest energy densities at the MEMS scale. And this makes them attractive for applications requiring large force and large displacement. The room for SMA improvement, though, is in the actuation bandwidth, or in other words, the rate at which these SMAs can be cycled has historically been limited, based on the rate at which you can get the heat into or dissipated out of your actuator. So one of the main focus areas of this dissertation then was on the development of nanoscale thickness SMA films to improve these device bandwidth limitations. In the culmination of this work, I was able to achieve up to 3 kilohertz of reversible actuation speeds, which is an order of magnitude improvement over conventional SMA. And this was enabled through the miniaturization of the SMA films. There are several issues that need to be addressed prior to successful fabrication of these SMA-based microactuators. This includes the development of suitable processing techniques to ensure a reversible phase change in the nanoscale thickness SMA. And additionally, suitable methods for ensuring a reliable two-way shape memory effect would be necessary to address consistent actuation over many cycles. So I had started with an extensive literature review in order to determine some of the existing methods in which to build a bilayer MEMS actuator with reversible shape change. So in order for this to happen, it's necessary to deform the SMA MEMS element in the martensitic phase. So here the graphic on the left-hand side captioned reversible shape change shows a chart including some of the extrinsic and intrinsic biasing mechanisms sufficient for reversible shape change. Although many options exist, I focused my design on the bilayer structure approach, which is boxed here in blue, primarily because it offers several advantages. These advantages include having design control over some parameters like the bilayer thicknesses, residual stress, and recovery stress, which can help impart specific curvature radius in the released SMA MEMS device. The mechanical construction would be possible in MEMS, but it's more complex, requiring integrated springs or dead weights or manual assembly, which is increasingly hard at these small scales. The intrinsic biasing mechanism shown in the right column focuses on exercising training or processing control over oriented precipitates or ion bombardment, which is not explicitly the focus here. The graphic on the right-hand side shows how the typical film stress and an SMA film changes as a function of temperature. And this is as the material is cycled between the martensite and austenite phases for a nickel titanium film on silicon substrate. The process would be similar for a released SMA-MEMS actuator, where these reversible deflections can be imparted due to the shape memory effect. So in pursuit of the size reduction in these nanoscale thickness SMA films, which would aid in actuation speed improvements, there does exist some imposing constraints, and those are shown here graphically. So interfacial diffusion regions exist at the NiTi silicon substrate interface, and this is due to the high temperature processing required to crystallize the SMA. And these factors can hinder shape memory effects in these localized regions. Also, the oxygen diffusion layer at the film surface is also crippling to shape memory effects because it changes the local composition of the nickel titanium alloy, which imposes additional interfacial constraints on the transformation or lowers the transformation temperature altogether. Grain size is also a critical factor, where it's generally established that grains below 80 to 100 nanometers will not exhibit the martensitic transformation. And this is due to additional physical constraints imposed by the grain boundaries, and eventually the volume of the grain is too small to even support a reversible phase change. So also, if you focus your attention on this graph of recovery stress and residual stress versus the film thickness, you'll see a couple of results that highlight these limitations. The recovery stress reaches some maximum value as the film thickness is reduced down, and this is typically around 700 nanometers to a micron in film thickness. And for films thinner than this, the recovery stress plummets extremely sharply or vanishes altogether in nanoscale thickness films. So the residual stress also takes on very large values in this nanoscale thickness range, and this highlights the interfacial regions with much higher residual stress due to the CTE mismatch between NiTi and silicon substrate, and then the high crystallization or annealing temperatures required to shape set the SMA in the first place. So each of these constraints shown here, as I said, impose limitations on the volume of material available to participate in the reversible phase change. So therefore, as shown in this figure on the right-hand side, typical best practices thus far has been to use sufficiently thick films of 1 or 2 microns or even thicker to increase the volume of material available and capable of undergoing a phase transformation. So in order for nanoscale SMA actuator volumes to exhibit shape memory effects, care must be taken to limit these constraints. So for example, lowering the deposition temperature could be expected to help alleviate some of the interfacial diffusion regions at this film substrate interface, and also reduce some of the interfacial strains due to CTE mismatch. And this is another focus area of this dissertation, namely reducing processing temperatures to 1, limit the interfacial diffusion, and 2, enable lower processing of SMA onto CMOS and polymer materials, which is currently limited by the high temperature processing steps required to crystallize the SMA films. So I would say here, the heart and soul of any successful PhD is no doubt these scientific and technical contributions. So here I lay out the 4 main contributions enabled by this body of work. First and foremost is that I developed methods to crystallize nanoscale thickness SMA films with shape memory effects at lowered processing temperatures to enable integration with CMOS and polymers. The second main contribution was identifying the processing conditions for obtaining NiTi films with microstructures capable of high frequency phase changes. This was done by careful examination of the shape memory properties and how they are impacted by a variety of the processing conditions listed here. The third contribution deals with building and characterizing shape memory effects using Bimorph architectures to control the NiTi actuator curvature radius and degree of unfolding. And this was primarily done using either NiTi on platinum and SU8 on NiTi actuators at the MEMS scale. So in each case, analytical modeling supplemented by experimental characterizations help to confirm or determine the bending radius in the bilayer stacks. And the fourth and final contribution deals with fast and low power actuation of SMA bilayers, where the SMA actuation frequency was shown for the first time to reach 3 kilohertz and at reversible actuation speeds, also requiring low voltage actuations, and finally a preliminary demonstration of a first of its kind SMA micromirror with large deflections. So in this section, I'll describe the methods developed to crystallize nanoscale thickness NiTi films with shape memory effects at lowered processing temperatures. So table 1 here, it shows the deposition parameters used to sputter nanoscale thickness NiTi films for this study. A slightly titanium-rich composition was chosen, which has been correlated to lowered crystallization temperatures in some other works. So NiTi films of 120, 225, and 450 nanometers were sputtered at 325 degrees. And films of 225 nanometers thickness were sputtered also at 400 and 600 degrees, which are generally more suitable temperatures to ensure the crystallization. Each of these depositions was done onto a silicon wafer, which had been coated with a 5 nanometer ruthenium seed layer by electron beam evaporation. The average grain size was measured in the B2 phase, as shown here in table 2, with a clear relationship of larger grains at higher deposition temperatures and longer deposition times. At the lowest deposition temperature of 325 degrees, the grain size increased from 25 nanometers in the thinnest film up to 70 nanometers in the 450 nanometer film. The largest grain sizes were measured in the 400 and 600 degree films, and this is consistent with the understanding that grain growth, or in other words, grain size, has a strong temperature dependence. So the main takeaway here is that samples were prepared allowing for characterization of the effects of thickness, grain size, crystallization temperature, and how these relate to shape memory properties in the nanoscale SMA films. So this is the characterization done using the film stress versus temperature technique. Figure A combines the stress curves for a constant film thickness of 225 nanometers for various deposition temperatures of 600, 400, and 325 degrees. The most pronounced stress curve, or in other words, the curve with exhibiting the largest recovery stress, in this case it was about 200 megapascals, and corresponded to the 600 degree sample. Figure B compares the stress curves for the constant deposition temperature of 325 degrees, and this was the lowest temperature considered in this study at various thicknesses. So here each film is undergoing the R phase to austenite transformation, and they're all pretty similar in terms of recovery stress, hysteresis, and transformation temperature. So the reversible transformation shown here, is shown to be above room temperature and centered around 60 degrees. And therefore these nanoscale SMA films would be suitable for microscale actuators operating at room temperature.
Cory, can I ask you a question?
Yeah.
Can you go back to so the upper and lower, the difference is, okay, anyway, I was wondering, so the hysteresis on this RU600 is pretty large.
It is. Yeah, and I would say, based on a variety of other characterizations we did, this film was undergoing the martensite austenite phase change, which is, characteristic of larger recovery stresses. You're absolutely right with this larger hysteresis. And again, that was for the highest deposition temperature for a 225 nanometer thickness film. I'm not sure if you can see my mouse here.
Yeah, it's moving. Yeah.
Okay. And then I'll also say, while we stop on this slide, the one done at 400 degrees, which is this black and gray curve, it's characteristic of this two-phase transformation. So, on heating, you've got the transformation between martensite and austenite. And then on cooling, I would almost say this is most likely due to this knee in the curve is the R phase transformation. It's characteristic of a narrower hysteresis. And then from this point on, you're going from this intermediate R phase down to a partial Martensitic transformation.
So this one with the really big hysteresis, that wouldn't be too good to use for the.
It really depends on what you're going for. So, you know, maybe some advantages of these narrow thermal hysteresis is you can get faster actuation.
Right.
But like with anything, it's a trade-off, right? You're going to get this faster actuation due to the narrow hysteresis, but you're compromising the recovery stress. And why that's significant is sometimes these larger recovery stresses are correlated to larger deflections. So there's a trade-off there, whether you're going for a fast actuation speed, you know, like high frequency actuation,
right.
or if you want to really get large deflections. And I would say the focus of this dissertation, we have reasons to explore both, or there's basically benefits for either case. I could take this red curve here and make an actuator that has a larger degree of unfolding due to the phase change. But of course, it's going to be slower,
right?
You know, when you actuate it, because it's got to go through this much larger temperature sweep to have this reversible deformation.
Yeah. Okay. Thanks.
So.
Yeah, trade-off, as you say. Yeah.
Yeah. Okay. So, you know, picking back up, this is, we're just looking at some additional characterization, same films that we were talking about. So this is XRD peak intensity in position versus temperature. So the phase transformation as a function of temperature was also observed by plotting this R phase peak intensity in A, and then peak position in B. The peak intensity for the R phase at room temperature was shown to vanish completely when heated above 60 degrees, and is consistent with the stress data, confirming that the transformation into this high temperature austenite phase was happening in each of these films. In B, there's a peak position shift between the 300 R phase at room temperature towards the 110 cubic phase of austenite at temperatures above 60 degrees. And this is also consistent with the stress data, directly confirming the transformation between austenite and R phase in each of these films. And that's including the films deposited at these relatively low temperatures of 325 degrees. This is looking at electrical resistivity measurements versus temperature. So these electrical resistivity measurements were made from room temperature up to 90 degrees. And the transformation temperatures were determined by looking at the derivative of resistivity with respect to temperature. In each of these films, the transformation was between austenite and R phase, and provided a third method of confirming that a nanoscale NiTi film deposited onto a ruthenium seed layer at temperatures as low as 325 degrees should be suitable for microactuation, and has promised to enable, you know, future integrations of these SMA films with CMOS and polymer materials. So in conclusion, for this first initial contribution, NiTi films with 120 nanometers thickness sputtered onto a ruthenium seed layer at temperatures as low as 325 degrees showed crystallization and XRD in reversible phase transformations above room temperature using stress and resistivity versus temperature measurements. The smaller grain size in these nanoscale films prevents the Martensitic phase transformation near room temperature and help to stabilize the R phase. The temperature-dependent phase transition from austenite to R phase was also observed for these NiTi films using 3 methods, confirming that low temperature processing of SMA films with a phase change should be extensible and enable, you know, greater integration with CMOS and polymer materials. I also list flexible electronics and soft body micro robotics. So this next section is highlighting the contribution number 2, which specifically enabled, or rather, I guess it was identifying the processing conditions for obtaining NiTi films with microstructures capable of high frequency phase changes. So all of the depositions were carried out in the ARL clean room using an AJA co-sputter tool. 4-inch targets of equiatomic NiTi and titanium were used to determine the sputtering parameters, which would yield equiatomic or slightly titanium-rich compositions. The equiatomic recipe turned out to require 375 watts of DC current applied to the NiTi target, and a simultaneous 250 watts of DC applied to the titanium target. A nominal deposition rate of 15 nanometers per minute was determined from using this process. And from there, I investigated a wide variety of sputtering pressures ranging from 2 to 10 millitorr, and substrate temperatures ranging from 325 degrees to 800 degrees. And then finally, this SEM equipped with EDAX was used to verify the film composition, generally to within 1 or 2 atomic percent. The stress temperature loops for NiTi on silicon wafer give us a good indication about the SMA film quality and their potential for MEMS actuator devices. So here I'm contrasting some different stress curves for 2 different deposition conditions. The red and blue curves are for NiTi deposited at 700 degrees, and the yellow-purple curves are for NiTi deposited at 800 degrees. So some of the characteristic differences is that the 800C deposition leads to not only a higher amount of recovery stress, but it also exhibits this narrow hysteresis knee in the curve upon cooling, which is characteristic of this intermediate R phase transformation. If you look at the dissertation, it goes into a lot more details about the TEM and additional X-ray diffraction characterization, but it's not included in this presentation, just in the interest of time. So many additional stress versus temperature plots for the NiTi on silicon wafer were generated using a variety of film thicknesses as shown here. So figures A and B, these are showing the thermal stress scans on the thicker films for which XRD showed significant volume fractions of the martensitic phase. And therefore these films had more significant changes in stress associated with this reversible phase change. Figure C shows 2 of the thinner NiTi films for which XRD still showed crystallization, but primarily austenite phase at room temperature. So a small amount of the film was able to undergo these thermal transformations. And therefore, you know, a hysteresis change was measured around 60 or 70 degrees. But at, you know, this was at diminished values of recovery stress. And these stress curves are characteristic of the R phase transformation, where recovery stress is small and hysteresis is narrow. This is all consistent with other data where films below 400 nanometers thickness have a tendency to exhibit the same transformation response as seen here. But these nonlinear changes in stress are later used to drive actuation in a MEMS bilayer device. So in this section, I identified the necessary processing conditions for obtaining NiTi films with microstructures capable of high frequency phase change. What I found is that recovery stress is much smaller in films below 400 nanometers thickness because the transformation is predominantly between R phase and austenite. Films of thickness between 500 nanometers and 1 micron or more, these generally had larger amounts of recovery stress and were thus more suitable for improved actuator performance. So this is contribution 3, and it was looking at fabricating stress bilayer MEMS actuators and characterizing the actuator curvature radius and degree of unfolding due to the shape memory effect. So I utilized 2 main approaches to fabricate these devices. So the first instance was NiTi sputtered onto platinum at high temperatures, which resulted in the CTE mismatch induced stress, which was suitable for curling the MEMS actuator after release from the substrate. In the second case, I spin coated SU8 on top of NiTi to achieve a similar effect. In this case, the CTE of SU8 is very large compared to NiTi, so therefore it makes up the top layer. When processed at high temperatures, the contraction of the SU8 on top of the NiTi causes the bilayer to curl upwards when released from the substrate. So the SMA MEMS actuators suitable for actuation based on these previous measurements were explored using the identified processing conditions in the earlier contributions. So the processing figure on the left-hand side here, I started with NiTi and sputtered it directly onto a platinum-coated silicon wafer. Ion mill etching was then used to pattern the NiTi platinum bimorph using standard photoresist and mask plates. Device release etch was done using xenon difluoride, which selectively etched the silicon wafer, but doesn't affect the NiTi and platinum. So residual stresses caused the bimorph to curl up after the device release. And the residual stresses are naturally influenced by the CTE mismatch between NiTi and platinum, and then the crystallization of the NiTi at high temperatures. Shape memory effects and their stress changes in the NiTi film is what caused the devices to actuate when subjected to heating. Then the figure on the right here shows the experimental setups, one of the many which was used to characterize the beam bending and actuation. A rate-controlled heater programmed a small heating stage where the MEMS chip was fastened, and using a high-resolution microscope, which was capable of tilting, was used to capture images and video of the thermal actuations. I found that by depositing a thin film of platinum underneath the NiTi, a bimorph structure that exhibited a curled state when released from the substrate can be thermally cycled to achieve the two-way shape memory effect. Then by studying different combinations of NiTi and platinum thicknesses and then comparing these results to an analytical model, I revealed that curvature was influenced by these parameters. So upon heating, then the NiTi platinum bimorph would actuate towards a substrate, the position in which they were shape set or annealed. So this slide overviews some of the characterizations done on this NiTi platinum bilayer actuator stack. Figure A is characteristic of the thermal actuation cycle for a typical NiTi platinum SMA-MEMS actuator. The cantilever array curls with some radius of curvature, and then when heated to 70 degrees, which was consistent with the stress versus temperature loops, the film undergoes a phase change, and therefore large nonlinear deflections downwards result from that. Upon cooling to room temperature, the actuation was shown to be fully reversible, which is characteristic of the two-way shape memory effect I had originally sought to achieve. Figure B shows the case where the NiTi and platinum layers were both thinned down. In this case, 600 nanometers of NiTi, which was half the original 1.2 microns in figure A, and then 20 nanometers of platinum, which was 10 times thinner than the original platinum thickness of 200. So the thickness reductions here allowed for a curvature radius of about 150 microns, which was a reduction close to a full order of magnitude from the 1.2 millimeters in the thicker stack. So the main takeaway here, I would say, is that the NiTi and platinum thickness ratio strongly influences the curvature radius. But in both cases, you know, a significant two-way shape memory effect was achieved using thermal cycling. So similar to growing NiTi on platinum, I had also showed that NiTi can be sputtered directly onto the silicon wafer, and then a layer of SU8 can be patterned and developed on top of the NiTi to achieve similar effects, namely allowing control over the curvature radius and actuation. So this section overviews some of the analytical techniques used to determine an optimal SU8 and NiTi thickness prior to going into the fabrication of SU8 on NiTi for the high frequency studies. So I'm presenting some of the equations used to model and to some extent optimize the curvature and degree of actuation of the SU8 and NiTi film stack. So the curvature term K is described by the biaxial elastic modulus of SU8 and NiTi, which is the E prime terms. And then thickness of the bilayer materials is described by the lowercase t terms. G is also a term involving the biaxial elastic modulus and thickness of the individual bilayer materials. Finally, it introduces this theta term, which accounts for the location of the neutral plane for the various film stacks. So then there's this epsilon term that describes the strain that arises due to CTE mismatch, and the delta T term, which arises from the high temperature processing effects on strain in the bilayer. So from these equations, a MATLAB script was generated and then ran through and solved for curvature and deflection due to the shape memory effect. So the contour plot here in this case, describes the deflections expected for a NiTi and SU8 cantilever bilayer of fixed length. In this case, the cantilever length is 300 microns as a function of the two design variables, the thickness of the SU8 on the left axis and the thickness of the NiTi on the bottom axis. The dark red region, or rather the darkest red region, corresponds to the maximum deflections expected, and the blue region represents the lowest deflections. The lower right region corresponds to a condition where the metallic SMA beam is thicker and thus more rigid, and imposes greater resistance to deflections induced by the shape memory effect. So overall, these results motivated the fabrication of a much thinner NiTi beam, as would be suitable to undergo more significant deflections during the actuation cycle. You can also see here that the SU8 layer should be sufficiently thin, in this case around 1 micron or less, to also stay within the dark red region. So the predicted condition for max deflection due to the shape memory effect was determined to be 824 nanometers of SU8 on top of 359 nanometers of NiTi. So this modeled result helped to influence the MEMS bilayer design based on this approach. The fabricated device parameters for NiTi and SU8 thicknesses that were actually built in the next section are marked with a star on this graph. And based on this contour map here, would be expected to exhibit significant amounts of deflection due to the phase change. Similar to calculating deflection, I was also interested to calculate the curvature of the MEMS device upon release from the substrate over a range of practical NiTi and SU8 thicknesses. So depending on the application space, the SMA, the MEMS could conceivably need to be released from substrate and maintain a flat orientation. Or in other applications, a bent beam with a specific, deflection or curvature radius would be more desirable. And that was the case for the micromirror array. So therefore, understanding how the NiTi and SU8 thickness ratios relate to beam curvature is also an important consideration for when designing the actuator. So this was an optimization problem in which I had assumed that a flat beam would most desirable, which ended up being the lower right of this contour map, and that's marked with a box here. Since the contour plot is curvature radius, a higher radius would correspond to a more flat configuration, which happened to correspond to the upper bound on NiTi thickness, which was 1.3 microns in this model, and then the lower bound for SU8 thickness, which was 200 nanometers due to processing limitations on getting SU8 to go any thinner than that. I would say this result is somewhat intuitive because the thicker NiTi would be expected to be more rigid, and then the thinnest SU8 configuration would minimize the bending due to CTE mismatch, which for NiTi and SU8 is quite large at about 40 parts per million. Since the fabricated device was in the blue region, a large amount of curling would be expected upon release from the substrate. And this was later proved to be the case with real device fabrications and measurements. And then this slide highlights some of those device fabrication parameters used to build the MEMS bilayer actuator based on SU8 and NiTi. So figure 1 shows the stress temperature loop for the SMA device wafer, exhibiting over 800 megapascals of recovery stress, which is a desired parameter for large deflections during the phase change. Table 1 lists the NiTi co-sputter parameters, which included a 600-degree crystallization temperature, an 18-minute sputter, and yielded a high-quality SMA film of 270 nanometers thick, which was pretty close to the optimal value according to the contour map a couple slides back. Table 2 lists the SU8 parameters used to target a film thickness on the order of 1 micron, where a 4,000 RPM spin speed resulted in 1 micron of SU8, which was also, intentionally close to the optimal value of 824 nanometers based on the contour maps I had shown. So this is looking at the fabrication of the bilayer MEMS structures capable of pulse actuation at higher frequencies. And the figure on the left-hand side shows how this bilayer actuator was built into a double beam resistor pattern, which would be suitable for inducing the shape memory effect by Joule heating. So beams with varied widths and lengths were fabricated using different designs on the mask plate. NiTi was patterned using photoresist and ion milling. And then SU8 was spun onto the wafer to a thickness of 1 micron and then patterned with an additional mask plate. It was the large CTE mismatch between the NiTi and SU8 combined with the high temperature curing of the SU8 that caused these interfacial strains to develop at the interface, which ultimately caused the bilayer MEMS device to curl upwards upon release from the substrate. So the SEM image in the upper right, it shows the curvature radius of the released actuator, exhibiting an out-of-plane curl, consistent with the model predictions shown earlier. A laser confocal measurement was used to quantify the curvature radius. In the lower right figure, it shows the actuator in the curled released state at room temperature and a radius of 178 microns. And then flattened out substantially to an actuated radius of 789 microns when heated above the austenite phase change temperature to 100 degrees. These experiments helped to confirm the two-way shape memory effect in this new device design based on SU8 and NiTi. From here, the next steps were to characterize the electrical actuation of the device, starting at low frequencies and progressing towards higher actuation frequency to explore how well this design would facilitate fast and reversible actuation. So the figure in the upper left, it plots the cantilever displacement versus the applied voltage. These curves were experimentally generated. Is there a question, or does somebody need to mute?
So a lot of the gun propulsion stuff you guys talked about.
Can everyone mute, please?
I don't think that's a question, Cory.
No, I think somebody just joined and needed to be
up.
muted.
Sorry, Cory, I just joined, but I'm muted, so I don't know what happened.
I gave you the mute. Yeah, I think we're good. So what I was saying is that these curves were experimentally generated using laser Doppler vibrometry technique, where a laser beam spot was focused onto the beam to monitor deflection over a range of applied voltages at low frequencies. So the shape memory effect was characterized by the large downward slope, which starts at about 0.3 volts and is fully actuated at half a volt. There's a symmetry about the 0 volts because the sweep went from positive and negative voltages at a slow rate of 2 hertz. The linear regions before and after the actuation are most likely due to the CTE mismatch between NiTi and SU8. And the magnitude of deflection is significantly more pronounced and over a very tight voltage interval, indicating that the Joule heating did induce a shape memory effect, which was sufficient to cause large and reversible two-way shape memory effects at low voltages. The figure in the upper right shows a pulsed actuation, which confirmed the reversible nature of these deflections. And the videos at the bottom show some of the demonstrations of the utility of these microactuator configurations. So the lower left figure shows the behavior of the two-way shape memory effect using a pulse voltage of 1 volt, which is still a significantly low voltage. The deflections are rather large at this MEMS scale and require small voltage thresholds to initiate the actuation. When these cantilevers are arrayed in parallel, such as figure to the lower right, the force would be expected to increase. And in this case, actuation is still fast and large, but the nature of this project was not so much concerned with applied forces, so these measurements were not pursued in this dissertation. The conclusions from this section of work were based on a comprehensive study of the two-way shape memory effects for 2 different bilayer configurations, one of which was the NiTi on platinum, and the other was SU8 on NiTi. In each case, an understanding of the deflection and curvature was validated with complementary experimental and analytical modeling. Curvature radius was shown to be tunable over a range of millimeter scale to micrometer scales, and reversible deflections due to the shape memory effects were considerable. These ultra-thin bilayer MEMS actuators were engineered to be sufficient to actuate quickly and at lower power levels using either laser irradiation or pulsed electrical currents to induce the phase change. And the fast actuation is the subject of my final main contribution. So this fourth and final contribution for this dissertation specifically enabled fast and pulsed electrical actuation, in addition to the passive laser actuation of the SMA-MEMS devices. Electrical actuation through Joule heating, coupled with nanoscale SMA films exhibiting good transformation properties and excellent heat sinking configuration, enabled these fast actuation speeds up to 3,000 hertz, which is faster than other historical works. Actuation thresholds were shown to be very low, requiring as little as ½ volt to initiate this reversible phase change. And finally, a first of its kind SMA micromirror was designed, fabricated, and shown to operate over 29.9 degrees using a nested microactuator design comprised of the SMA film actuator. So here it was demonstrated that the green laser could supply enough heat energy to actuate the NiTi SMA MEMS in a rapid fashion. The actuation followed a 1/I² trend, where I is the laser intensity. And the actuation time was shown to vary between about 100 milliseconds at lower fluences and on the order of 1 to 2 watts per centimeter squared. And it could happen as quickly as few milliseconds if the optical fluence was 10 watts per centimeter squared or more. So these actuation speeds were enabled by the extremely small nature of the NiTi SMA MEMS actuator. As you can see in the video, the two-way shape memory effect is initiated by a laser scanning over the cantilever array, a process that is fast and reversible upon heating and cooling. So in order to further characterize the electrical performance of the various SMA MEMS Joule-Heaters, voltage current sweeps were generated for the different geometry devices. This allowed for calculation of the device resistance, which was a useful parameter to feed into some additional Joule heating simulations in COMSOL. I saw, based on these characterizations, that the current draw was rather low. It ranged anywhere from about 2 milliamps up to 15 or 20 milliamps, but depended on the applied voltage load. This would mean that the power draw is also quite low. The slopes of the IV curves were used to generate these table of resistance values, and it matched the expected trend. So in other words, the widest beam with shortest length exhibited the least electrical resistance, in this case about 25 ohms. But by comparison, the narrowest and longest beam exhibited the highest electrical resistance of 173 ohms. So this experiment was done to understand the high frequency actuation. So I was looking to see what are the fundamental limitations in regards to actuation speed in these SMA MEMS Joule heater devices. I want to point out that, as shown in the introduction slides, a comprehensive literature review was done and showed that SMA actuation frequency up to this point has historically been quite low, no more than a few hundred hertz. And this is owing to the fact that the two-way shape memory effect only works when the device can be completely heated and cooled through one full actuation cycle. And the heat transfer rates ultimately limit how fast the typical SMA MEMS actuators can be cycled. So in these curves, by pulsing a 1 volt signal, which was a square wave with 50% duty cycle, at 500 hertz and 1,000 hertz, I measured the same maximum deflection. In this case, it was 550 nanometers, and that's shown in the two figures on the left. These plots show displacement versus time, like was originally shown at the lower frequencies for the earlier characterizations, to confirm the two-way shape memory effects. The sharp dips and rises in this curve are indicative of the reversible shape change. So at 2 and 3 kilohertz, this deflection becomes progressively less, and this is due to the heat not being fully input or fully removed from these higher operating frequencies. So at 2 kilohertz, the max deflection had reduced from about 550 down to about 490 nanometers. And at 3 kilohertz, the max deflection was only about 300 nanometers. And based on these characterizations, a measured rise time, approximately 400 microseconds, was determined during during a full heating actuation cycle. At these higher frequencies, most likely only a partial shape memory effect was being induced, and this was by heating and cooling through a smaller temperature range within the SMA hysteresis loop.
What was the input signal like? Was it triangular too, or square? Or?
In this case, it was. I mean, for the published paper, it was only looking at a square wave with 50% duty cycle.
So does the deflection look exactly like the input, or there's some response that's different from the input signal?
I don't think I have them overlaid, but I think the response is more or less the same.
I see. But this ringing that you have is some response effect, I guess, right?
Yeah, I guess if you look here, I had determined that there it is. This is due to the mechanical resonance of the beam.
I see.
If I remember right, I think that was around. I want to say the resonance was around 30 kilohertz. So that's what each of these is here. It's resonating at 30 kilohertz.
Okay. Thanks.
Sure. So, addition to the experiments, a COMSOL heat transfer model was also used to help understand the rise time due to heating and the decay time due to cooling. So a physical model of the SU8 NiTi Joule-Heater was constructed and included standard material properties of the NiTi and SU8. When a 1-volt electrical bias was placed across the 2 electrodes, the Joule heating reached a steady state temperature in about 400 microseconds, which was very consistent with what was measured in the experiments. Similarly, the temperature upon removing the voltage source was mapped over time, and the steady state temperature was reached in a similar 400 microsecond time scale as well. So in this section, I'm coming back to one of the overarching goals of this dissertation. The challenge was to design these fast MEMS actuators based on nanoscale SMA films to enable a new class of large deflection micromirrors. So to this end, a demonstration based on all of the contributions leading up to this point enabled the design, build, and testing of a first of its kind SMA-MEMS micromirror. So the figure on the left provides a top-down view of the proposed micromirror array in a nominally open position. And for optical modulation or beam steering applications, this would serve as an open diode, meaning most of the light is freely to propagate through. The figure on the right shows the closed mirror array, which would not allow for the light to pass. So this approach could be suitable for adaptive imaging or beam steering, as is commonly used in LiDARs based on MEMS micromirrors. One could also imagine, a configuration where individual mirrors could be selectively actuated with independent electrical input to each pixel, or each pixel could be partially or fully actuated in phase or out of phase, depending on the intended requirement for whatever application. So these SEMs here, these were taken on fabricated and released SMA MEMS micromirror devices. The actuator arm was designed to have alternating segments of bent, rigid, and bent beams, and this was to impart more overall curvature in the beam and a larger deflection in the micromirror. So these beam segments were comprised of active SMA, which could undergo the shape memory effect to drive the micromirror. The rigid segments were comprised of a thicker photoresist, and that was in order to just limit bending in those regions. And the key takeaway here is that this novel nested hinge design enabled larger mirror deflections in a smaller footprint, which is more suitable for tightly packed mirror pixels. So using the laser confocal microscope, a 3-dimensional image of the full shutter pixel was recorded at room temperature in the unactuated condition, and at 100 degrees on a hot plate in the actuated position. So this allowed for a line scan to be plotted to assess the deflection or angle of the micromirror in each of the actuated and unactuated positions. So this device actuated from a starting angle of a positive 23.3 degrees. It went through flat, or 0 degrees, down to a maximum tilt of negative 6.6 degrees. And this corresponded to a total tilt angle change of 29.9 degrees. And this is relatively large compared to typical digital micromirror devices, where deflection is usually limited to around 12 degrees of tip tilt. So as a final demonstration of this initial motivation, I was able to build these large scale micromirror arrays on a silicon wafer. The dimensions of the active array here are 4 millimeter by 4 millimeter with 150 micron pixel size. This rapid laser actuation was achieved using a diffuse laser beam and the visible band. And because the beam was diffusely focused over the entire array, each of the pixels actuated more or less simultaneously. When the laser was turned off, the actuation was shown to be reversible. So overall, the two-way shape memory effect was achieved for a few cycles on these mirrors. So the demonstration using static heating on a hot plate and the dynamic laser heating here served as a preliminary proof of principle, which enabled a patent application to be filed and in detailing the methods and manufacture and operation. As this was only a preliminary demonstration, I would say there remains much future R&D to be done to refine some of the designs and operation. And if successfully developed, integration of these mirrors into a variety of systems or application spaces could ultimately benefit the defense and commercial sectors. And this would include applications in adaptive optics, beam steering, LiDAR, or medical imaging. So in conclusion, you know, the final significant contribution of this dissertation has shown that two-way shape memory effects and nanoscale thickness SMA MEMS has sufficiently enabled some scientific and technical advancements related to low power, large deflection, and high frequency microactuators and micromirrors for a variety of applications relevant to defense and commercial industries. So overall, this effort progressed from the early stages, which focused on ensuring crystallization and nanoscale thickness SMA films based on this nitinol alloy, which enabled the design and fabrication of fast actuators with tailored curvature, and ultimately led to a first ever demonstration of an SMA micromirror array with micrometer sized pixels. This is a list of publications that document this work. And that wraps up the defense. So at this point, you know, thank you everyone for your attention, and I'll be happy to answer any questions.
All right, many thanks, Cory. So this is the time where